explain to me what eigenvalues and eigenvectors are. Okay, so if Shudeng wants me to write something on the board here, which I'm more than happy to do.
Then the value of one part will be the eigenvalue and the vector x will be I.
So Shudeng says that lambda is an eigenvalue, it's a scalar, and that x is an eigenvector. Sometimes you hear them referred to as characteristic roots and characteristic vectors. They all mean the same thing. How do we find, from what Shudeng has given us, how do we find lambda? You know what a determinant is? We talked about it before. And we talked about systems of homogeneous equations. Is this a system of homogeneous equations? In order for that system of homogeneous equations to have a unique solution for x, what has to be true about the rank of the matrix in parentheses? Oh, let me tell you what the dimensions of things are. The dimension of A, we're going to make t by t. The dimension of x, we're going to make t by 1. Lambda is a scalar, it's 1 by 1. And x is t by 1 instead. So x is still t by 1. A is still t by t. So what's the dimension of the identity matrix? If A is t by t, lambda is a scalar, then the identity matrix has to have what dimension? T by t. So the whole thing in parentheses has what dimension? T by t. So everything in parentheses is t by t. So I have a system of linearly homogeneous equations. So what do you know about the rank of the thing in parentheses, given everything that preceded it tonight? There's got to be a unique solution for x. So can it be rank t? It has to be less than t, right? So if the rank of the matrix in parentheses is less than t, what's the determinant of the thing in parentheses? So the determinant of the thing in parentheses has to be 0, right? And so we can look at the determinant of that thing, and we can solve for the set of lambdas that makes that true. And once we have the lambdas, we can go back and solve for the characteristic vectors by imposing a simple restriction that each characteristic vector have a length of 1. Explain to the assembled multitude what's happening. A is the basis for a vector space, right? What's the relationship between the characteristic vectors and the vectors in A that form the basis of this subspace? You told me that, listen carefully, you told me that A spans a vector space. That means that the columns of A form the basis of a vector space. Okay? And we know how to figure out the characteristic vectors. So the set of x's, which are the characteristic vectors, have what relationship to the vectors in A, which are the basis of a vector space? What were we doing when we derived the characteristic vectors, or the eigenvectors? Pretty hard question. In the past, have you ever had to figure out the characteristic roots and characteristic vectors for a matrix? Have figured out the characteristic roots and characteristic vectors of a given matrix. So you know how to do the arithmetic. But nobody ever stopped to ask you the question of, what is it that's actually happening here? Everybody was happy just to see you go through the arithmetic, pushing your pencil around on a piece of paper, right? Everybody else has been through the same experience, right? How do you figure out characteristics and vectors of a matrix? Nobody ever stopped to ask you what you were really doing. Not the way I asked it, right? The two columns in A are the basis of a vector space. Since A is a full column rank, how many characteristic vectors does it have? 2. So are those two vectors linearly independent of one another? Yeah. So they form the basis of another vector space. What's the relationship between, let's call the two characteristic vectors, x1 and x2. What's the relationship between these two columns, which form the basis of a vector space, and the two characteristic vectors that we just derived? x1 and x2 are orthogonal to one another, yeah. And remember from the bad old days when you first had to figure out the set of lambdas and then you had to figure out the corresponding x's, x1 and x2, you imposed the restriction that x1 transpose x1 is equal to 1 and x2 transpose x2 is also equal to 1. So they are orthonormal and they're of unit length. Are these two columns orthonormal? Is the inner product between this column and this column 0. No. But they are independent of one another. So they're not at right angles to one another, and we understand orthogonality. Is this vector of unit length? No. It looks like it's 4 plus 1 is 5, the square root of 5. Is this one of unit length? No, it's the square root of 10. But these two guys, x1 and x2, they're of unit length. And you told me that x1 is orthogonal to x2. So what did we do? Yeah, we took the columns of A, which form the basis of the vector space. And the first thing we did was spread them apart so they're at 90 degrees to one another. And then we rescaled them so that they were of unit length. Pretty cool, huh? So we took A, the columns of which, or the rows, talk about it either way. We took A, the columns of which form the basis of a vector space, and that basis was not orthonormal. With the characteristic vectors, we created a new vector space in which the basis was orthonormal. That is, well, I erased one of the pictures already. We went from here to a picture where the ellipse was lined up along the axis, and then we went to here. Didn't change the fact that the original quadratic form is this ellipse that's tilted off the axis. That's still true. We just rescaled things and turned them a little bit to make them more convenient and easier to understand. So what we could do is we could get the set of characteristic vectors, find their square root. So if the set of characteristic vectors is C, we could put X transpose C, C transpose A, C transpose C, X. That's the characteristic vectors. C transpose A, C transpose gives me a matrix that has the characteristic roots on the main diagonal. They're not all equal. That's how I got the ellipse. But the off diagonals are 0. So I went from this ellipse to the ellipse where it was lined up properly along the axes. And I was calling, I erased too much. I said that's going to be Y, that's going to be Y transpose, and we could make that B for the same argument. And then I can, remember, I'm always free to multiply by the identity matrix, and I'm free to define the identity matrix in whatever way I want. So I could I could stick in on either side the inverse of the square roots of the characteristic roots. And then the part in the middle all becomes 1s, and the part on the edges becomes distance. I've got a circle. So this Q,
The middle term there is a B.
is the same as this one. Here? Yeah, I should have a B here. Or I should have a B here, and a D here.
Isn't B supposed to be C transpose AC transpose or C transpose AC? It is.
I like to transpose on both.
Okay.
I don't know enough about the fact